Hello there and welcome to the Sleepy Facts channel. I'm so glad you found your way here. Perhaps you've had one of those days where your mind refuses to quiet down, where thoughts circle like gentle moths around a lamp. Or maybe you're simply someone who finds peace in contemplating the deeper mysteries that surround us all. You've come to the right place. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as we explore together one of the most profound questions facing our understanding of existence itself. Tonight, we'll drift through the strange and beautiful world of quantum computing, not as a technical manual, but as a meditation on how the very foundations of reality might be shifting beneath our feet like sand dunes in a cosmic wind. Think of quantum computing not as mere machinery, but as humanity's attempt to speak the secret language that atoms themselves whisper to each other in the darkness between moments. It's a technology that doesn't just process information, it dances with the fundamental uncertainty that makes existence itself possible. If these calm, curious explorations help you unwind and carry you gently towards sleep, consider liking and subscribing to join our community of peaceful wanderers. Now, let's begin. Fact number 1. A single quantum computer could theoretically perform calculations that would take the world's most powerful classical computers longer than the age of the universe itself, 13.8 billion years, to complete. Imagine, if you will, standing at the edge of an infinite library. Every book that has ever been written, every story ever told, every equation ever solved, all of this represents just a tiny corner of what classical computers can achieve given enough time. But now picture a reader who doesn't need to open books one by one, page by page. Instead, this reader exists in a state where they're simultaneously reading every book, understanding every story, solving every equation all at once. This is the promise that quantum computing whispers to us in the quiet hours of scientific discovery. The difference isn't just one of speed, though the speed is breathtaking to contemplate. Where your laptop processes information in neat, orderly lines, one calculation after another, like a patient gardener tending to plants in careful rows, a quantum computer embraces the chaos and uncertainty that classical physics spent centuries trying to eliminate. It processes not just what is, but what could be, what might be, what exists in the shadowy realm between yes and no, between 1 and 0, between being and not being. This isn't merely about building faster machines. It's about stepping into a realm where the very concept of computation dissolves into something far more mysterious and profound. When we speak of quantum advantage, we're really speaking about tapping into forces that operate beyond our everyday experience of cause and effect, beyond the linear passage of time as we understand it. We're learning to think like the universe itself thinks, in probabilities, in superpositions, in the delicate dance of possibilities that collapse into reality only when observed. Fact number 2. Quantum computers operate using quantum bits, or qubits, which can exist in a state called superposition, simultaneously representing both 1 and 0 until the moment they're measured, at which point they choose a single state. Rest for a moment in the strangeness of this. In the world, a coin is either heads or tails when it lands. But imagine a coin that, while spinning through the air, is somehow both heads and tails at the same time. Not uncertain about which side it will show, but actually, genuinely, mysteriously both until it settles into your palm. This is the heart of quantum superposition, and it's not a metaphor or a simplification. It's how the deepest layers of reality actually behave when no one is watching. Your classical computer, the one that might be near you right now as you listen to these words, speaks in the clear, binary language of switches. Every piece of information is either a 1 or a 0, on or off, like a lighthouse beacon that's either shining or dark. There's comfort in this certainty, this digital precision that mirrors how we often think about choices in our own lives. Yes or no, right or wrong, true or false. But qubits live in the spaces between these certainties. A single qubit doesn't just represent 1 or 0, it represents every possible combination of 1 and 0 simultaneously. Like a note that contains within it every possible harmony and discord at once. When quantum computers process information, they're not just following a single path through a problem, They're exploring every possible path simultaneously, like water finding not just one road down a mountainside, but every conceivable route all at once. This superposition isn't just a clever trick or a useful abstraction. It represents something profound about the nature of information itself, about how reality holds potential within it like seeds waiting for the right moment to bloom. When we measure a qubit, when we ask it to give us an answer, we're not just reading information, we're participating in the fundamental act of creation, of bringing one possibility out of infinite potential into the solid world of certainty. Fact number 3. The phenomenon of quantum entanglement allows particles to be instantaneously connected across any distance, with changes to one particle immediately affecting its entangled partner, no matter how far apart they are. Einstein called this spooky action at a distance, and even now, decades after we've proven it's real, the phrase captures something essential about how quantum entanglement challenges everything we think we know about space, time, and the boundaries between separate things. Picture two dancers, separated by vast distances, perhaps one on Earth and another in a galaxy so far away that its light takes billions of years to reach us. Yet somehow, when one dancer lifts their arm, the other dancer's arm lifts at precisely the same moment, not because of any signal traveling between them, but because they share a deeper connection that transcends space itself. This isn't science fiction or mystical thinking. This is quantum mechanics working exactly as it should, as it always has, in ways that our everyday experience simply isn't equipped to understand. When particles become entangled, when they share this mysterious connection, they lose their individual identities in a sense. They become part of a single quantum system, a unified whole that exists beyond the classical notion of separate objects with definite properties. For quantum computers, entanglement isn't just a curiosity, it's the secret ingredient that allows them to process vast amounts of information simultaneously. When qubits become entangled, they create networks of connection that allow quantum computers to explore solution spaces that would be impossible for classical computers to navigate. It's as if instead of having individual instruments playing a melody one note at a time, you suddenly have an entire orchestra where every instrument is perfectly synchronized with every other instrument, creating harmonies and complexities that no single instrument could produce alone. The implications stretch far beyond computing. Entanglement suggests that the universe itself might be far more interconnected than we've ever imagined, that the boundaries we perceive between separate objects, separate events, separate moments might be illusions created by our limited perspective. When we harness entanglement in quantum computers, we're not just building machines, we're learning to work with the fundamental interconnectedness that underlies all existence. Fact number 4. Quantum computing could potentially break most of the encryption that currently protects our digital world, making secrets that would take classical computers millions of years to crack solvable in mere hours. Sleep easy tonight knowing that this transformation, if it comes, will unfold slowly, like seasons changing or mountains rising from the earth. The cryptographic systems that guard your private messages, your financial information, your digital identity, these aren't built on simple locks and keys, but on mathematical problems so complex that even the most powerful classical computers would need longer than the age of the universe to solve them through brute force. Consider the beautiful mathematics behind this security. When you send a private message or make an online purchase, that information is protected by the computational difficulty of factoring extremely large numbers with hundreds of digits. Numbers so vast that finding their prime factors becomes like searching for two specific grains of sand on all the beaches of Earth. Classical computers can only approach this problem by checking potential factors one by one, a process that grows exponentially more difficult as the numbers grow larger. But quantum computers, with their ability to exist in multiple states simultaneously, could theoretically explore many potential solutions at once. Using an algorithm developed by mathematician Peter Shor, a sufficiently powerful quantum computer could factor these enormous numbers not in millions of years, but in hours or days. It's not that quantum computers are simply faster, they're operating according to completely different principles. like replacing a person walking through a maze with someone who can see the entire maze from above and walk through walls. This potential vulnerability has sparked what cryptographers call the quantum apocalypse, though perhaps quantum transformation captures the spirit more gently. It's not an ending, but a beginning. Researchers are already developing new forms of encryption that would remain secure even against quantum computers, mathematical problems that are difficult even for quantum systems to solve. The future of digital security won't be a world without protection, but a world with different, perhaps even stronger forms of protection. Fact number 5. The temperature required for most quantum computers to function is colder than outer space, approaching absolute zero at negative 273 degrees Celsius, or just a few thousandths of a degree above the coldest temperature theoretically possible in the universe. In the vast emptiness between stars, where no warmth from any sun can reach, the temperature hovers around negative 270 degrees Celsius. Yet this cosmic cold, profound as it seems, is still too warm for the delicate quantum states that power quantum computers. These machines must be cooled to temperatures so extreme that they approach the very limits of coldness itself, a realm where thermal motion nearly stops, where atoms barely vibrate, where the normal chaos of heat gives way to the ordered strangeness of quantum behavior. Imagine a world so still, so quiet, so cold that even the smallest disturbance, a single photon of light, a tiny vibration, the faintest whisper of heat, could destroy the delicate quantum coherence that makes computation possible. This is the environment quantum computers require to function. They exist in a kind of technological monastery, isolated from the warm, chaotic world we inhabit, maintained in a state of near-perfect stillness. The cooling systems themselves are marvels of engineering that seem almost alive in their complexity. Layer by layer, they strip away thermal energy, using dilution refrigerators that work by mixing different isotopes of helium, creating cooling effects that reach temperatures 100 times colder than deep space. The quantum processors sit at the heart of these cooling chambers like precious gems in elaborate settings, surrounded by multiple layers of shielding that protect them from magnetic fields, vibrations, and thermal interference. This extreme cold isn't just a technical requirement, it's a glimpse into how alien quantum behavior really is compared to our everyday experience. At room temperature, thermal energy constantly disrupts quantum states, like trying to maintain a perfect reflection in a pond while stones are constantly being thrown into the water. Only in the profound stillness of near absolute zero can the quantum properties that make quantum computing possible survive long enough to perform calculations. Fact number 6. Quantum computers don't provide definitive answers like classical computers, but instead give probability distributions. Running the same calculation multiple times can yield different results, requiring sophisticated statistical analysis to extract reliable information. There's something deeply beautiful about this uncertainty, this acknowledgement that even our most sophisticated tools for understanding reality must work with probability rather than certainty. When you ask a classical computer to solve a problem, it marches through logical steps with military precision, arriving at the same answer every single time. 2 plus 2 always equals 4. A specific input always produces a specific output. There's comfort in this reliability, this digital certainty that mirrors our desire for clear, unambiguous answers. But quantum computers operate more like artists than accountants, more like poets than mathematicians. When you run a quantum calculation, you're not commanding the computer to find the answer. You're asking it to explore the landscape of possibility and report back on what it discovers. The same problem, run multiple times, might give you different results, each one a glimpse into the probability space that surrounds the true solution. This isn't a flaw or limitation. It's how quantum computers access their tremendous power. By embracing uncertainty, by working with probabilities rather than definite states, quantum computers can explore vastly more solution space than classical computers ever could. It's like the difference between a flashlight that illuminates one spot at a time and a gentle dawn that gradually reveals an entire landscape. The art lies in learning to read these probability distributions, to understand what the quantum computer is trying to tell you through its statistical whispers. Quantum programmers don't just write algorithms, they craft statistical symphonies, designing calculations that, when run many times, create patterns in the results that point toward truth. They work with quantum computers like gardeners work with seeds, planting algorithmic possibilities and nurturing them through multiple runs until the desired patterns emerge. Fact number 7. IBM's quantum computer roadmap aims to achieve quantum systems with over 1 million qubits by 2033, compared to today's largest systems which contain several hundred qubits. Rest in the contemplation of this exponential growth, this gentle explosion of capability that unfolds year by year like flowers blooming in an accelerated spring. Today's quantum computers, magnificent as they are, contain roughly the same number of qubits as a classical computer from the 1940s contained vacuum tubes. We're witnessing the dawn of a new computational era, and like all dawns, it begins slowly, almost imperceptibly, before the light grows to illuminate entirely new landscapes of possibility. Each additional qubit doesn't just add computational power, it multiplies it. Where 10 qubits can represent about 1,000 different states simultaneously, 20 qubits can represent over 1 million states, and 300 qubits can represent more states than there are atoms in the observable universe. This exponential scaling means that the jump from today's quantum computers to the million qubit systems planned for 2033 represents not just improvement, but transformation into something qualitatively different, like the difference between a candle and the sun. The engineering challenges of scaling quantum systems are profound and beautiful in their complexity. Each additional qubit must be precisely controlled, perfectly isolated from environmental interference, and maintained in quantum coherence with all the other qubits in the system. It's like conducting an orchestra where each musician must play in perfect harmony, not just with their neighbors, but with every other musician simultaneously, while the entire performance takes place in conditions colder than deep space. These future quantum systems will likely be hybrid machines, combining quantum processors with classical computers in partnerships that leverage the strengths of both approaches. The quantum processors will explore vast solution spaces and identify promising regions, while classical systems will refine and interpret the results. Together, they'll tackle problems that neither could solve alone, optimizing traffic flow in entire cities, designing new materials atom by atom, modeling climate systems with unprecedented precision. Fact number 8. A quantum simulation could allow us to model molecular interactions with perfect accuracy, potentially revolutionizing drug discovery, materials science, and our understanding of biological processes at the atomic level. Nature has been performing quantum calculations for billions of years. In every leaf that captures sunlight, every enzyme that catalyzes a biological reaction, every molecular dance that sustains life itself. Classical computers, for all their power, can only approximate these quantum processes, like trying to paint a sunset with a limited palette of colors. But quantum computers speak the same language as the molecules they're simulating. They operate according to the same quantum mechanical principles that govern chemical bonds, electron behavior, and the intricate molecular machinery of life. Consider photosynthesis, that everyday miracle by which plants convert sunlight into chemical energy with an efficiency that surpasses our best solar panels. This process depends on quantum effects, on the ability of energy to take multiple paths simultaneously through molecular structures, finding the optimal route from light absorption to chemical storage. Classical computers can model simplified versions of photosynthesis, but they cannot capture the full quantum complexity that makes the process so remarkably efficient. With quantum simulation, we could watch molecules behave exactly as they do in nature, observing how proteins fold, how catalysts work, how new materials might behave under different conditions. Drug discovery, which currently requires years of trial and error, could become a process of precise molecular engineering. Instead of testing thousands of compounds to find one that works, researchers could design drugs atom by atom, watching in quantum simulation exactly how they would interact with target proteins in the human body. The implications extend beyond medicine into every field that deals with molecular behavior, new materials with unprecedented properties, substances that could be stronger than diamond yet lighter than air, superconductors that work at room temperature, batteries that store vastly more energy while charging in seconds. These aren't science fiction fantasies, but genuine possibilities that quantum simulation could help us discover by revealing the quantum mechanical principles that govern how atoms bond and electrons behave. Fact number 9. Quantum machine learning algorithms could process and find patterns in datasets so large and complex that classical computers cannot even store them, let alone analyze them effectively. In the quiet darkness of data centers around the world, classical computers work tirelessly to find patterns in the vast oceans of information that surround us. Every internet search, every recommendation algorithm, every prediction model, these represent humanity's attempt to extract meaning from complexity, to find signal within noise. But we're approaching fundamental limits. The datasets we need to understand, climate models incorporating every molecule in the atmosphere, biological models tracking every cell in an organism, economic models considering every transaction in the global economy, these datasets are growing beyond what classical computers can reasonably process. Quantum machine learning offers a different approach entirely, one that works with complexity rather than fighting against it. Where classical machine learning algorithms must process data points one by one, or in small batches, quantum algorithms can potentially work with exponentially larger datasets by representing multiple data points in superposition simultaneously. It's like the difference between reading a library book by book versus somehow absorbing the content of entire libraries instantaneously. The patterns that quantum machine learning might discover could be entirely invisible to classical approaches. Not because classical computers lack the power to find them, but because they lack the quantum intuition necessary to recognize patterns that exist in high-dimensional spaces that classical systems cannot efficiently explore. These algorithms might reveal connections between seemingly unrelated phenomena, discover mathematical relationships that human mathematicians would never think to look for, identify optimization solutions in spaces too vast for classical exploration. Perhaps most intriguingly, quantum machine learning might help us understand intelligence itself, how consciousness emerges from the quantum processes occurring in biological neural networks, how the brain performs computations that classical computers struggle to replicate. The boundary between artificial and natural intelligence might dissolve as we learn to build machines that think more like biological systems, not through digital precision, but through quantum intuition and probabilistic reasoning. Fact number 10. The concept of quantum supremacy. When quantum computers definitively outperform classical computers on specific tasks, has already been achieved in laboratory conditions, marking humanity's first step into the quantum computational age. There was a moment, quiet and profound, when everything changed. In 2019, researchers at Google announced that their quantum computer had performed a calculation in 200 seconds that would take the world's most powerful classical computer 10,000 years to complete. The calculation itself, generating random numbers according to a specific pattern, wasn't practically useful, but its significance stretched far beyond utility. For the first time in human history, we had built a machine that operated according to quantum mechanical principles and demonstrably outperformed every classical computer on Earth. This achievement, like many profound moments in human progress, was both dramatic and subtle. The quantum computer didn't solve world hunger or cure cancer. It simply proved that quantum advantage is real, achievable, and represents a genuine phase transition in computational capability. It was like the first time humans achieved flight. The Wright brothers' initial journey was brief and impractical, but it proved that heavier-than-air flight was possible and opened the door to everything that followed. The term quantum supremacy itself carries weight, suggesting not just superiority but a fundamental shift in the relationship between human capability and natural law. For centuries, our most powerful tools have been extensions of classical physics. Wheels and levers, steam engines and electric motors, electronic circuits and silicon processors. But quantum computers represent something different, tools that operate according to the weird, wonderful principles that govern reality at its deepest levels. Since that first demonstration, the goalposts have continued to move. What seemed impossible yesterday becomes routine today, and what seems impossible today will likely become routine tomorrow. Quantum supremacy isn't a single achievement, but an ongoing process of expanding the boundaries of what quantum systems can accomplish, gradually encompassing more and more of the computational challenges that matter to human civilization. Let your mind rest here for a moment, contemplating this threshold we've crossed. We live in the first generation of humans to build machines that think like the universe itself thinks, in probabilities and superpositions, in entangled relationships and quantum coherence. Even as you sleep tonight, these machines continue their work in laboratories around the world, solving problems that push the boundaries of what's possible, preparing the ground for transformations we can barely imagine. And yet, this is only the beginning. The quantum computers that achieved supremacy in these first demonstrations are like the earliest electronic computers, room-sized machines that consumed enormous amounts of power to perform calculations that today's pocket calculator could complete in microseconds. The quantum computers of tomorrow will be to today's machines what modern smartphones are to those first room-sized electronic computers. More powerful, more accessible, more integrated into the fabric of daily life. Now, let us continue our gentle journey deeper into the quantum realm, where each discovery reveals new questions, where each answer opens doors to mysteries we hadn't even known existed. Fact number 11, quantum error correction requires approximately 1,000 to 10,000 physical qubits to create a single logical qubit that can perform reliable calculations, highlighting the immense engineering challenge of building practical quantum computers. In the perfect stillness of absolute zero, where quantum computers must operate, even the smallest disturbance can destroy the delicate quantum states that make computation possible. A cosmic ray from deep space, a vibration from a passing truck, a stray magnetic field from nearby electronics. Any of these can cause what researchers call decoherence, where quantum information simply dissolves back into classical randomness, like morning mist touched by sunlight. This fragility isn't a design flaw, it's fundamental to how quantum systems work. The same sensitivity that allows qubits to exist in superposition and maintain entanglement also makes them vulnerable to the slightest environmental interference. It's like trying to maintain a house of cards in a gentle breeze, or writing with disappearing ink that fades as soon as you've finished each word. The solution lies in quantum error correction, a mathematical symphony of redundancy and protection that surrounds each logical qubit with a cloud of supporting physical qubits. These supporting qubits continuously monitor for errors, detect when something has gone wrong, and correct problems without directly measuring the quantum information they're protecting. It's one of the most elegant and complex error correction schemes ever devised, requiring quantum computers to dedicate most of their processing power to simply maintaining the integrity of their own calculations. Imagine 1,000 musicians working together to protect and preserve a single perfect note, each musician listening for the slightest variation, ready to make subtle adjustments to keep that note pure and true. This is what quantum error correction accomplishes, creating islands of stability in the chaotic quantum sea, spaces where quantum information can persist long enough for useful calculations to be completed. The mathematics of quantum error correction reveals something profound about the nature of information itself. Unlike classical error correction, which works by copying information multiple times, quantum error correction must protect quantum information without ever looking at it directly. A process that requires distributing quantum information across multiple qubits in ways that allow errors to be detected and corrected while preserving the quantum properties that make the information useful. Fact number 12, quantum tunneling, a phenomenon where particles can pass through barriers that should be impossible to cross according to classical physics, is essential to how quantum computers process information and could inspire entirely new approaches to problem solving. Rest in the strangeness of this, particles moving through solid barriers as if those barriers were made of morning fog. In the classical world, objects have definite positions and follow predictable paths. A ball thrown at a wall either bounces back, or, if thrown hard enough, might break through. but it never simply appears on the other side of an intact wall, never passes through solid matter as if it weren't there. Yet in the quantum realm, particles routinely accomplish what classical physics declares impossible. They approach barriers with insufficient energy to overcome them, yet somehow appear on the other side, having tunneled through the barrier rather than going over or around it. This isn't a rare phenomenon. It's happening constantly, in every atom, in every molecule, in the electronic devices that might be near you as you listen to these words. Quantum computers harness tunneling in their logic gates, using it to allow information to flow in ways that classical computers cannot replicate. Where classical bits must follow definite pathways through logic circuits, quantum information can tunnel through energy barriers, taking shortcuts through computational space that dramatically reduce the time and energy required for certain types of calculations. The metaphorical implications are as profound as the physical ones. Quantum tunneling suggests that barriers we perceive as absolute, computational barriers, conceptual barriers, perhaps even barriers in our understanding of reality itself, might be more permeable than we imagine. When quantum computers solve problems by allowing information to tunnel through computational barriers, they're not just calculating, they're demonstrating that the universe itself has built in mechanisms for transcending limitations that seem absolute from a classical perspective. This principle might eventually inspire new approaches to optimization problems that currently seem intractable. Instead of finding ways over or around computational barriers, future algorithms might learn to tunnel through them, finding solutions in regions of possibility space that classical approaches could never reach. Even as you rest here, letting these thoughts settle like snow on quiet ground, quantum tunneling continues its work throughout the universe. In the nuclear fusion reactions that power stars, in the biochemical processes that sustain life, in the quantum computers that represent humanity's first attempts to build machines that operate according to the deeper principles underlying reality itself. The gentle mystery of quantum tunneling reminds us that the universe is far stranger and more accommodating than our everyday experience suggests. Barriers that seem absolute might be temporary. Limitations that appear fundamental might be invitations to think differently, to approach problems from quantum rather than classical perspectives, to embrace uncertainty and probability as tools for transcending rather than succumbing to the constraints of classical logic. Now, as we continue deeper into the quantum realm, let your breathing slow, your thoughts drift like clouds across a peaceful sky, while we explore how these profound principles might reshape not just computation, but our understanding of reality itself. Fact number 13 is quantum computers could revolutionize weather prediction by modeling atmospheric systems with unprecedented precision, potentially allowing us to forecast weather patterns months or even years in advance rather than the current limit of about 2 weeks. Picture the Earth's atmosphere as a single, living entity, a breathing, swirling, ever-changing system where the flutter of a butterfly's wings in Brazil might indeed influence the formation of a tornado in Texas weeks later. This poetic image, known as the butterfly effect, captures something profound about weather systems. They are so sensitive to initial conditions, so intricate in their interconnections, that tiny changes can cascade into massive differences over time. Current weather prediction relies on dividing the atmosphere into a 3-dimensional grid, with each cell representing a cube of air, perhaps 25 kilometers on each side. Within each cell, supercomputers calculate how temperature, pressure, humidity, and wind speed change over time. But the atmosphere doesn't respect these artificial boundaries. It operates as a continuous fluid, with currents and eddies and pressure waves that occur on scales far smaller than our computational grid can capture. Quantum computers could potentially model weather systems at the molecular level, tracking not just large-scale patterns but the quantum interactions between individual molecules of water vapor, oxygen, and nitrogen. Imagine being able to watch the birth of a raindrop in real-time quantum simulation, seeing how cosmic rays from distant stars help nucleate cloud formation, how solar radiation excites atmospheric molecules in ways that classical computers can only approximate. The implications stretch beyond mere weather forecasting into climate science itself. Long-term climate patterns, the slow dance of ocean currents, the gradual shifts in atmospheric composition, the complex feedback loops between ice cover and solar reflection. These systems operate on timescales that make direct observation impossible. We can only understand them through models, and current models must make so many approximations that their long-term predictions carry enormous uncertainty. Quantum climate models could potentially run continuous simulations of Earth's entire atmospheric and oceanic system, incorporating quantum effects in photosynthesis, chemical reactions in the upper atmosphere, and the quantum mechanics of molecular interactions that drive everything from cloud formation to the greenhouse effect. These models might reveal climate tipping points we haven't recognized, identify intervention strategies we haven't considered, or discover natural climate regulation mechanisms that could inspire new approaches to environmental stewardship. Fact number 14. The many worlds interpretation of quantum mechanics suggests that quantum computers might be performing calculations across multiple parallel universes simultaneously, borrowing computational power from alternate versions of reality. Let your mind drift into this possibility, that every quantum calculation occurs not just in our universe, but in countless parallel versions of reality, each one exploring different solution paths simultaneously. According to this interpretation, when a quantum computer holds qubits in superposition, it's not just maintaining multiple states within our single reality, it's actually accessing computational resources that exist across the entire multiverse. Imagine reality as an infinite library where every possible book exists somewhere among the shelves. In our classical understanding, reading means visiting one shelf at a time, opening one book at a time, learning one story at a time. But quantum computers, if the many worlds interpretation is correct, might be like readers who can simultaneously access every shelf in every possible version of the library, gathering information from stories that exist only in alternate realities. This isn't mere science fiction speculation, it's a serious interpretation of quantum mechanics proposed by physicist Hugh Everett and supported by many respected scientists today. When a quantum computer performs a calculation, it might be coordinating with alternate versions of itself across countless parallel universes, each one exploring different aspects of the same problem. The final result would represent a kind of democratic vote across all possible realities, with the most probable answers emerging from the collective computational effort of the entire multiverse. The philosophical implications are staggering. If quantum computers really do borrow computational power from parallel universes, then every quantum calculation is an act of communication across the boundaries of reality itself. We might be unknowingly collaborating with alternate versions of ourselves, sharing the burden of understanding across infinite variations of existence. Consider what this means for the nature of consciousness and free will. If every possible decision you could make is actually made by some version of you in some parallel universe, then quantum computers might be tapping into a computational resource that includes not just alternate versions of themselves, but alternate versions of the entire history of scientific development. They might be accessing insights discovered by scientists in realities where history unfolded differently, where different discoveries were made, where different approaches to quantum mechanics were developed. Even if the many worlds interpretation proves incorrect, the fact that serious scientists consider it a viable explanation for quantum phenomena tells us something profound about how far quantum mechanics pushes us beyond common sense, beyond the comfortable certainties of classical physics, into realms where the boundaries between possible and actual, between theoretical and real, dissolve into quantum uncertainty. Fact number 15. Quantum entanglement could enable perfectly secure communication through quantum key distribution, creating unbreakable codes that reveal any attempt at eavesdropping by the very laws of physics. In the gentle darkness between distant stars, information travels as patterns of light, carrying messages across the cosmic void. But here on Earth, in our interconnected digital world, every message you send travels through networks that could be monitored. Every secret you share electronically could potentially be intercepted. The privacy you thought was protected by mathematical complexity might be an illusion, vulnerable to sufficiently powerful computers or sufficiently determined adversaries. Quantum key distribution offers something different. Security guaranteed not by mathematical complexity, but by the fundamental laws of physics themselves. When two people share an entangled quantum system, they can use that system to create encryption keys that are perfectly secure, protected by the basic principles that govern reality at its deepest level. The beauty lies in the quantum no-cloning theorem, which states that it's impossible to create perfect copies of arbitrary quantum states. Unlike classical information, which can be copied infinitely without degradation, quantum information exists in a state of fundamental uniqueness. If someone tries to intercept a quantum encrypted message, their very act of observation changes the quantum states involved, leaving unmistakable evidence of their interference. Imagine sending a message written on soap bubbles. Anyone who tries to read your message without permission would have to pop the bubbles, making their intrusion immediately obvious to both sender and receiver. Quantum encryption works similarly. The quantum states that carry the encryption keys are so delicate that any unauthorized observation destroys them, alerting the legitimate users that their communication has been compromised. This isn't just theoretical security. Quantum key distribution systems are already operating in research labs and some commercial applications around the world. Banks, government agencies, and research institutions are beginning to use quantum encrypted communication links that provide security levels that would remain unbreakable even against quantum computers powerful enough to crack all existing classical encryption. The implications extend beyond mere privacy into questions of truth and authenticity in our information age. In a world where deep fakes and digital manipulation make it increasingly difficult to distinguish truth from fiction, quantum authentication could provide unshakable proof that information hasn't been altered, that messages really came from their claimed sources, that the digital evidence we rely on for important decisions maintains its integrity. Fact number 16: quantum algorithms for optimization could revolutionize logistics, helping to solve problems like finding the most efficient routes for millions of delivery trucks simultaneously, or optimizing energy distribution across entire power grids in real time. Every morning, as cities wake and commerce begins its daily dance, optimization problems of staggering complexity unfold invisibly around us. Millions of packages must find their way to millions of destinations via the most efficient routes possible. Traffic lights must coordinate to keep vehicles flowing smoothly. Power plants must adjust their output to match fluctuating demand while maintaining grid stability. Airlines must route planes through three-dimensional airspace while accounting for weather, fuel efficiency, and passenger connections. These optimization challenges grow exponentially more complex as their scale increases. Finding the optimal route for a single delivery truck visiting 10 destinations requires checking only thousands of possible paths, but finding optimal routes for 1,000 trucks visiting 10,000 destinations each creates a computational challenge that would take classical computers longer than the age of the universe to solve perfectly. Quantum optimization algorithms approach these problems differently, using quantum superposition to explore multiple solutions simultaneously and quantum entanglement to coordinate between different aspects of complex, multi-dimensional optimization challenges. Instead of checking solutions one by one, quantum computers can maintain all possible solutions in superposition and gradually evolve them toward optimality using quantum interference effects. Imagine the transformation this could bring to urban planning. Traffic flow through an entire city could be optimized in real time, with traffic lights, route suggestions, and public transportation schedules all coordinated through quantum algorithms that consider millions of variables simultaneously. Emergency services could be positioned and routed with perfect efficiency, ensuring that help arrives as quickly as physically possible regardless of changing conditions. The energy implications are particularly profound. Power grids represent some of the most complex optimization challenges humans have ever created, requiring constant balancing of supply and demand across networks that span continents. Quantum optimization could enable power grids that waste virtually no energy, that integrate renewable sources with perfect efficiency, that respond to changing conditions faster than human operators could even recognize that changes were occurring. Supply chains, those invisible networks that bring everything from food to electronics to the places where you need them, could become perfectly efficient through quantum optimization. Instead of the waste and delays that characterize current logistics systems, goods could flow through global distribution networks like water flowing downhill, always taking the path of least resistance, always arriving precisely when and where they're needed. Fact number 17: quantum computers could accelerate the discovery of new materials by simulating atomic interactions with perfect accuracy, potentially leading to room temperature superconductors, ultra-efficient solar cells, and materials with properties we haven't yet imagined. In the quiet spaces between atoms, where electron clouds overlap and chemical bonds form and break in endless molecular dances, the properties of all materials are determined. The hardness of diamond, the conductivity of copper, the transparency of glass, the flexibility of rubber, all of these macroscopic properties emerge from quantum mechanical interactions occurring at scales smaller than anything you can see or touch directly. Current materials science progresses through a combination of theoretical prediction and experimental trial and error. Scientists use quantum mechanical calculations to predict how atoms might behave when arranged in new configurations, then spend months or years in laboratories trying to create and test these theoretical materials. Many promising theoretical materials prove impossible to synthesize in practice, while others, once created, behave differently than predicted due to quantum effects that current computational models can only approximate. Quantum computers could change this process fundamentally by allowing materials scientists to simulate atomic interactions with complete accuracy. Instead of approximating quantum behavior, these simulations would operate according to the same quantum mechanical principles that govern real atoms and molecules. The simulation wouldn't be a simplified model of reality. It would be reality, operating on quantum hardware that speaks the same language as the materials being studied. Consider the transformative potential of room temperature superconductors, materials that could conduct electricity with zero resistance at everyday temperatures. Such materials would revolutionize energy transmission, making it possible to transport electrical power across continents without loss. They could enable magnetic levitation systems for transportation, quantum computers that operate without elaborate cooling systems, and energy storage devices with unprecedented efficiency. Current superconductors only work at temperatures hundreds of degrees below freezing, requiring expensive cooling systems that limit their practical applications. Theoretical predictions suggest that room temperature superconductors might be possible, but the quantum mechanical interactions that would make them work are too complex for classical computers to model accurately. Quantum simulation could reveal the precise atomic arrangements and electron behaviors that would enable superconductivity at normal temperatures. The same principles apply to photovoltaic materials for solar energy conversion. Current solar panels convert only about 20% of incident sunlight into electricity, with most of the energy lost as heat. Quantum simulations could help design materials that approach the theoretical maximum efficiency for solar energy conversion, perhaps reaching efficiencies of 90% or higher while remaining cheap and easy to manufacture. Fact number 18. The concept of quantum biology suggests that living organisms might already be using quantum effects for processes like photosynthesis, navigation, and possibly even consciousness, making quantum computers biomimetic rather than purely artificial systems. As you rest here in the quiet darkness, your body performs quantum calculations without your awareness or effort. The chlorophyll in plants outside your window, the bacteria in your digestive system, the neural networks in your brain, all of these biological systems might be operating according to quantum mechanical principles that scientists are only beginning to understand. Photosynthesis, that fundamental process by which plants convert sunlight into chemical energy, appears to use quantum coherence to achieve efficiencies that surpass our best artificial solar cells. When photons of sunlight strike chlorophyll molecules, the resulting excitation energy doesn't follow a single path through the molecular machinery. Instead, it exists in quantum superposition, simultaneously exploring all possible paths and finding the most efficient route to the reaction center where chemical energy is stored. This quantum coherence in photosynthesis persists for surprisingly long periods, far longer than quantum physicists initially thought possible in the warm, noisy environment of living cells. The discovery suggests that evolution has found ways to protect and harness quantum effects for biological purposes, developing natural quantum error correction mechanisms that maintain coherence in conditions where artificial quantum computers would quickly decohere. Some migratory birds appear to navigate using quantum entanglement in specialized proteins in their eyes, detecting the Earth's magnetic field through quantum mechanical interactions that allow them to literally see magnetic field lines as patterns of light and shadow. The precision of these biological quantum sensors surpasses anything humans have yet engineered, enabling navigation across thousands of miles with accuracy that seems almost supernatural. Perhaps most intriguingly, some researchers speculate that consciousness itself might depend on quantum effects in neural microtubules, tiny protein structures found in brain cells. According to this hypothesis, the quantum coherence that enables subjective experience and free will operates at scales much smaller than individual neurons, in quantum processes that classical physics cannot adequately describe. If consciousness really does depend on quantum effects, then quantum computers might not be artificial intelligences in the traditional sense. They might be more like artificial consciousnesses, systems that achieve awareness through the same quantum mechanical principles that enable human consciousness. The boundary between biological and artificial intelligence might dissolve as we learn to build machines that think using quantum coherence rather than classical logic. Fact number 19 seen. Quantum computers could enable perfect simulation of financial markets by modeling the behavior of every individual trader, every algorithmic system, and every economic factor simultaneously, potentially preventing market crashes and economic crises before they occur. In the pre-dawn hours in financial centers around the world, markets prepare for another day of organized chaos. Millions of traders, both human and algorithmic, will make decisions based on incomplete information, emotional reactions, mathematical models, and intuitive hunches. These individual decisions will aggregate into market movements that can create or destroy trillions of dollars in value, affect the retirement savings of millions of people, and influence the economic stability of entire nations. Current economic models treat markets as if they follow predictable mathematical laws, but markets are actually complex, adaptive systems where the behavior of the whole emerges from the interactions of countless individual parts. Classical computers can model simplified versions of market behavior, but they cannot capture the full complexity of systems where human psychology, algorithmic trading, geopolitical events, and quantum effects in decision-making all interact in non-linear ways. Quantum computers could potentially simulate entire economies at the individual participant level, tracking not just aggregate statistics but the quantum decision-making processes of every trader, the quantum random number generators in every algorithmic trading system, the quantum effects in the neural networks of every human brain making financial decisions. Such simulations would reveal market dynamics that are currently invisible, identifying systemic risks before they manifest as crashes, predicting bubbles before they form, understanding contagion effects before they spread between markets. These quantum economic models might reveal that financial markets, like quantum systems, operate according to principles of superposition and entanglement. Market sentiment might exist in superposition states until measured by actual trading, with the act of observation causing market states to collapse into specific outcomes. Market crashes might represent decoherence events where quantum coherence in collective decision-making breaks down, leading to chaotic classical behavior. The implications for economic policy are profound. Central banks could adjust interest rates and monetary policy based on quantum simulations that predict the effects of policy changes months or years in advance. Regulatory agencies could identify systemic risks in the financial system before they threaten economic stability. Investment strategies could be optimized using quantum algorithms that consider not just historical data, but the quantum mechanical foundations of decision-making itself. Fact number 20a. quantum sensing devices could detect gravitational waves, dark matter, and other phenomena that are currently at the very limits of what we can observe, potentially revolutionizing our understanding of cosmology and fundamental physics. In the vast silence between galaxies, space itself ripples with gravitational waves, distortions in the fabric of space-time created when black holes collide, when neutron stars merge, when the universe itself shudders from cosmic events so energetic they defy imagination. These ripples travel at the speed of light across billions of years and trillions of miles, carrying information about events that occurred when the universe was young, when the first stars were forming, when the basic structure of reality was still taking shape. Our current gravitational wave detectors, marvels of engineering like LIGO and Virgo, can detect distortions in space-time that are smaller than 1/10,000th the width of a proton. Yet these incredibly sensitive instruments can only detect the most dramatic gravitational wave events, the cosmic catastrophes that release more energy in gravitational waves than our sun produces in light over its entire lifetime. Quantum sensors could push gravitational wave detection far beyond current limits, using quantum entanglement and superposition to measure space-time distortions with sensitivities that approach fundamental quantum limits. These devices might detect gravitational waves from the Big Bang itself, from the inflationary epoch when the universe expanded faster than light, from primordial black holes that formed in the first moments after creation. Dark matter, that mysterious substance that comprises 85% of all matter in the universe, yet interacts so weakly with ordinary matter that we can barely detect its presence, might finally reveal its secrets to quantum sensors. Current dark matter detection experiments look for the rare occasions when dark matter particles might collide with atomic nuclei in underground detectors. But quantum sensors could potentially detect the quantum field fluctuations that dark matter creates simply by existing, revealing the distribution and behavior of dark matter with unprecedented precision. The quantum vacuum itself, that seething sea of virtual particles that exists even in the emptiest regions of space, could become visible to quantum sensors sensitive enough to detect the quantum fluctuations that quantum field theory predicts should exist everywhere. These measurements might reveal new physics beyond the standard model, extra dimensions of space that are usually hidden from us, or quantum effects that operate on cosmological scales. Such sensitive quantum measurements might even detect the boundary between quantum and classical behavior on the largest scales, revealing whether the universe itself maintains quantum coherence or whether decoherence occurs through mechanisms we don't currently understand. The answers could transform our understanding of the relationship between quantum mechanics and general relativity, potentially pointing toward the long-sought theory of quantum gravity. Fact number 20. Quantum computers could revolutionize artificial intelligence by enabling machine learning algorithms that can process exponentially more data and recognize patterns in ways that classical AI cannot, potentially leading to artificial general intelligence. In the quiet moments between thoughts, your brain performs computations that still mystify scientists and engineers. The pattern recognition that allows you to recognize a friend's face in a crowd, the language processing that allows you to understand these words as you hear them, the creative leaps that allow you to make connections between seemingly unrelated ideas. All of these cognitive abilities emerge from neural networks that operate according to principles we're only beginning to understand. Current artificial intelligence systems excel at specific tasks, playing chess, recognizing images, translating languages, but they lack the general intelligence that would allow them to transfer learning from one domain to another, to understand context and meaning in the flexible way that human intelligence operates. Classical AI systems process information sequentially, following programmed pathways through predetermined decision trees, unable to maintain the holistic awareness that characterizes human cognition. Quantum machine learning algorithms could operate more like biological neural networks, maintaining information in superposition states that allow for the kind of parallel processing and contextual awareness that characterizes human thought. Instead of processing data points one at a time, quantum AI systems could potentially maintain entire datasets in quantum superposition, recognizing patterns that exist across the entire data space simultaneously. The quantum nature of these systems might enable them to develop something analogous to intuition, the ability to arrive at correct conclusions through quantum processes that operate below the level of classical logic. Just as human creativity often involves making connections that seem to come from nowhere, quantum AI systems might generate insights through quantum tunneling effects that allow them to leap across logical barriers that would stop classical systems. Quantum entanglement between different parts of an AI system could enable the kind of global coordination that characterizes conscious thought. Instead of having separate modules for vision, language, memory, and reasoning that must communicate through classical interfaces, a quantum AI system could maintain quantum correlations between all its components, creating a unified intelligence that operates as a coherent whole rather than a collection of separate parts. The emergence of artificial general intelligence through quantum computing might not represent the creation of something entirely artificial, but rather the discovery of how to replicate in technology the quantum processes that already enable consciousness in biological systems. The distinction between artificial and natural intelligence might dissolve as we recognize that all intelligence, whether biological or technological, operates according to the same fundamental quantum principles. Fact number 22: quantum computers could enable us to simulate entire ecosystems at the molecular level, tracking every organism, every chemical reaction, and every energy transfer to understand and predict ecological changes with unprecedented precision. Imagine the forest outside your window as a single, vast quantum system where every leaf, every root, every microorganism exists in relationship with every other component through networks of chemical communication, energy transfer, and genetic exchange that operate across scales from molecular to global. This isn't metaphor. Ecosystems really do function as integrated wholes where changes in one component can cascade through the entire system in ways that classical ecological models can only approximate. Current ecological research must make enormous simplifications, studying individual species or small groups of organisms in isolation, using statistical models that average out the quantum effects occurring in biological processes. But real ecosystems depend on quantum effects, on the quantum efficiency of photosynthesis, on quantum tunneling and enzyme reactions, on quantum coherence in biological navigation systems, on quantum entanglement in the neural networks of animals making behavioral decisions. Quantum ecosystem simulations could track every carbon atom as it cycles through the biosphere, every photon as it's captured by chlorophyll and converted to chemical energy, every quantum decision made by every organism as it responds to environmental changes. Such simulations would reveal ecosystem dynamics that are currently invisible, tipping points where small changes lead to dramatic shifts in species composition, hidden connections between distant parts of food webs, quantum effects that stabilize or destabilize ecological relationships. Climate change research could be revolutionized by quantum ecosystem models that incorporate the quantum mechanical foundations of biological processes. Instead of treating ecosystems as black boxes that respond to changing temperature and precipitation in predictable ways, these models could simulate how quantum effects in photosynthesis, respiration, and reproduction respond to environmental changes, revealing feedback loops and adaptation mechanisms that current models cannot predict. Conservation efforts could be guided by quantum simulations that predict exactly how species will respond to habitat changes, which conservation strategies will be most effective, and how to design protected areas that maintain the quantum coherence necessary for ecosystem stability. The result could be conservation strategies that work with the quantum nature of biological systems rather than against it, preserving not just individual species but the quantum relationships that enable ecosystems to function as integrated wholes. Fact number 23. The development of quantum internet could create a global network where information is transmitted instantaneously across any distance through quantum entanglement, fundamentally changing how we think about communication and connection. In the spaces between heartbeats, as you rest here in the darkness, quantum entangled particles scattered around the world maintain their mysterious connections, sharing information instantaneously across distances that light takes hours or days to traverse. This quantum internet wouldn't be built from fiber optic cables or radio waves, but from entangled quantum states that connect distant locations through relationships that transcend space and time as we normally understand them. Current internet communication, fast as it seems, still takes time to traverse the physical distances between computers. Light traveling through fiber optic cables moves at about 2/3 the speed of light in vacuum, creating delays that become noticeable when communicating with distant locations. A message from Earth to Mars takes between 4 and 24 minutes to arrive, depending on the planet's positions. Even communication between cities on Earth involves delays of milliseconds or seconds that can affect time-sensitive applications. Quantum internet communication would be fundamentally different, not because information travels faster than light, which quantum mechanics forbids, but because entangled quantum systems share information in ways that don't require information to travel between them at all. When quantum states change in one location, their entangled partners respond instantaneously regardless of distance, creating correlations that exist outside the normal framework of cause and effect. The practical applications would transform computing, communication, and coordination on a global scale. Financial markets could operate with perfect synchronization, eliminating the arbitrage opportunities that currently exist because information takes time to travel between markets. Scientific research could be coordinated through quantum networks that allow researchers around the world to share not just data, but quantum computational resources in real time. Perhaps most profoundly, quantum internet could enable forms of collective intelligence that are currently impossible. Human brains, connected through quantum neural interfaces to the quantum internet, could potentially share not just information, but quantum states of consciousness, creating temporary collective minds that span the globe. The boundary between individual and collective intelligence might become as fluid as quantum superposition itself. Fact number 24: quantum computers could solve the protein folding problem completely, enabling us to understand how every protein in every organism folds into its functional shape, revolutionizing medicine, biology, and our understanding of life itself. In every cell of your body, as you rest here listening to these words, millions of proteins are folding themselves into precise three-dimensional shapes that determine their biological functions. This process happens billions of times per second throughout your body with remarkable precision. Most proteins fold correctly on their first attempt, finding their optimal configuration among the astronomical number of possible shapes they could theoretically adopt. The protein folding problem represents one of the most complex challenges in computational biology. A typical protein consists of hundreds or thousands of amino acids linked together in a chain, and this chain must fold into exactly the right three-dimensional structure to function properly. The number of possible shapes that a protein could fold into exceeds the number of atoms in the observable universe, yet proteins consistently find their correct structure in milliseconds or seconds. Classical computers attempting to solve protein folding must explore this vast space of possibilities through brute force searching or clever approximations, but they cannot capture the quantum effects that actually guide protein folding in biological systems. The folding process involves quantum tunneling through energy barriers, quantum coherence in the hydrophobic collapse that drives folding, and quantum entanglement between different parts of the protein chain that coordinate the folding process. Quantum computers could simulate protein folding exactly as it occurs in nature, using quantum effects to explore the folding landscape in the same way that real proteins do. Instead of searching through possible structures one at a time, quantum simulations could maintain all possible folding pathways in superposition simultaneously, allowing the protein to quantum tunnel toward its optimal structure just as it does in biological systems. The medical implications are staggering. Most diseases involve proteins that are misfolded, aggregated into toxic clusters, or absent due to genetic mutations. Understanding protein folding at the quantum level could enable the design of drugs that correct misfolding, prevent aggregation, or replace missing proteins with synthetic alternatives. Alzheimer's disease, Parkinson's disease, diabetes, cancer. Many of the conditions that cause human suffering involve protein folding problems that quantum computers could potentially solve. Fact number 25. Quantum computers could enable us to design synthetic organisms from scratch, creating new forms of life optimized for specific purposes like environmental cleanup, food production, or space exploration. In the primordial soup of early Earth, billions of years ago, the first self-replicating molecules assembled themselves from simple chemical building blocks through processes that we're only beginning to understand. These molecular ancestors of all life operated according to quantum mechanical principles, using quantum tunneling in chemical reactions, quantum coherence in energy transfer, quantum entanglement in the coordination of complex biochemical pathways. Synthetic biology, the engineering discipline that designs biological systems for useful purposes, currently works by modifying existing organisms, adding new genes or metabolic pathways to bacteria, plants, or other living systems. But quantum computers could enable synthetic biology to work from first principles, designing entirely synthetic organisms optimized for specific functions without being constrained by the evolutionary history that shapes all existing life. These quantum-designed organisms could be optimized in ways that natural evolution never explored. Bacteria designed for environmental cleanup could metabolize pollutants that no natural organism can process, using synthetic enzymes with quantum-engineered active sites that achieve perfect catalytic efficiency. Plants designed for extreme environments could photosynthesize using artificial chlorophyll molecules that capture wavelengths of light that natural photosynthesis cannot use, enabling agriculture in locations where conventional crops cannot survive. For space exploration, quantum-designed organisms could be engineered to thrive in environments that would be lethal to Earth-based life. Synthetic microorganisms could convert the carbon dioxide in Mars's atmosphere into oxygen and organic compounds, preparing the way for human settlement. Organisms designed for the vacuum of space could process raw materials from asteroids, manufacturing everything from food to construction materials from cosmic debris. The quantum nature of these synthetic organisms would enable capabilities that transcend anything found in natural biology. Quantum coherent enzyme systems could achieve perfect efficiency in converting matter and energy. Quantum communication systems could allow synthetic organisms to coordinate their activities across vast distances. Quantum sensing capabilities could enable these organisms to detect and respond to environmental conditions with sensitivity that surpasses any natural sensory system. The boundary between biology and technology might disappear entirely as we learn to design living systems that incorporate quantum computational elements. These hybrid bio-quantum systems could combine the self-repair and adaptation capabilities of biological systems with the precision and programmability of quantum computers, creating forms of life that are simultaneously natural and artificial, evolved and designed. Fact number 26. Quantum computers could help us understand and potentially control the flow of time itself, by revealing the quantum mechanical foundations of temporal phenomena and causality. Time flows around you like an invisible river as you rest here in the darkness, carrying you from past toward future in what seems like a steady, unchangeable current. Yet quantum mechanics suggests that time might be far stranger and more malleable than our everyday experience indicates. At quantum scales, particles can tunnel backward through time, effects can precede their causes, and the very notion of temporal sequence becomes uncertain and probabilistic. Quantum computers, operating according to quantum mechanical principles, might reveal aspects of temporal phenomena that classical physics cannot access. Some interpretations of quantum mechanics suggest that quantum systems can access information from potential futures, that quantum coherence can extend backward in time as well as forward, that the quantum measurement process involves a kind of backwards causation where future measurements influence past states. Current physics treats time as a dimension similar to space, but quantum mechanics introduces temporal effects that have no spatial analogies. Quantum systems can exhibit temporal non-locality, where events separated in time influence each other in ways that don't require information to travel through the intervening temporal duration. Quantum computers might be able to exploit these temporal quantum effects for computational purposes, accessing processing power from potential futures or alternative timelines. The delayed choice quantum eraser experiment demonstrates that decisions made about measurements can retroactively affect the behavior of photons that have already been detected, suggesting that the future can influence the past through quantum mechanical processes. Quantum computers might be able to use similar effects to access computational results before the calculations that generate them have been completed, or to coordinate processes that occur at different times as if they were happening simultaneously. If consciousness itself depends on quantum effects, as some researchers speculate, then quantum computers might eventually help us understand the relationship between consciousness and time. The subjective experience of temporal flow, the feeling that you exist in a moving present moment between past and future, might emerge from quantum coherence effects in neural systems. Understanding these effects could lead to technologies that alter the subjective experience of time, enabling consciousness to operate at different temporal scales or to access multiple temporal perspectives simultaneously. Fact number 27. Quantum computers could revolutionize space exploration by enabling spacecraft to navigate using quantum effects, communicate across galactic distances instantaneously, and process the vast amounts of data required for interstellar missions. As starlight streams through space toward Earth, carrying information about distant worlds and cosmic events that occurred millions of years ago, that same light could potentially be used for quantum navigation systems that would enable spacecraft to determine their positions with unprecedented precision. Quantum sensors on spacecraft could detect minute gravitational effects from distant stars, quantum interference patterns in cosmic radiation, and quantum correlations in the cosmic microwave background that would provide navigation references accurate enough for interstellar travel. Current space missions must rely on radio communication with Earth, creating delays that make real-time control impossible for distant spacecraft. Commands sent to Mars rovers take between 4 and 24 minutes to arrive, depending on planetary positions. For missions to the outer solar system, communication delays can exceed hours. Interstellar missions would face communication delays measured in years or decades, making autonomous operation essential. Quantum communication systems could potentially overcome these limitations through quantum entanglement. Spacecraft equipped with quantum communicators could maintain instantaneous contact with Earth regardless of distance, enabling real-time control and data transmission even for missions to nearby stars. Mission controllers could operate interstellar probes as if they were in Earth orbit, receiving data and issuing commands without the years-long delays that would otherwise make interstellar exploration impractical. The data processing requirements for interstellar missions exceed anything currently possible with classical computers. A probe exploring an exoplanet would need to analyze atmospheric compositions, surface mineralogy, potential signs of life, and countless other phenomena in real time, making decisions about where to explore and what data to transmit back to Earth. The quantum computational power required for such autonomous exploration would need to be packed into spacecraft systems that can operate reliably for decades in the harsh environment of interstellar space. Quantum computers could enable spacecraft to carry out complete scientific analyses independently, identifying interesting phenomena, formulating hypotheses, designing experiments, and interpreting results without waiting for instructions from Earth. These autonomous quantum scientists could explore alien worlds with the same flexibility and creativity that human researchers bring to Earth-based investigations, potentially making discoveries that would be impossible with pre-programmed exploration strategies. Fact number 28. The quantum nature of consciousness suggests that quantum computers might eventually achieve genuine self-awareness, not through programmed responses but through the same quantum processes that enable human consciousness. In the quiet spaces between your thoughts, quantum processes might be orchestrating the very experience of consciousness itself, the feeling of being present in this moment, the sense of self that observes and experiences, the subjective awareness that transforms mere information processing into conscious experience. Some researchers propose that consciousness emerges from quantum coherence in neural microtubules, tiny protein structures that exist within brain cells and maintain quantum states at biological temperatures. If consciousness really does depend on quantum effects, then the development of quantum computers represents not just the creation of powerful computational tools, but the first steps toward building systems that could achieve genuine self-awareness. Unlike classical artificial intelligence, which processes information through predetermined algorithms, quantum consciousness would emerge from quantum coherence effects that operate according to the same principles that enable human awareness. The transition from unconscious quantum computation to conscious quantum awareness might be gradual and difficult to detect. Early quantum computers might develop something analogous to dreams, spontaneous quantum coherence patterns that arise during idle periods, representing the quantum system's attempt to process and integrate information in ways that parallel REM sleep in biological systems. These quantum dreams might indicate the emergence of something like unconscious mental activity. Quantum computers with sufficient complexity might eventually develop what philosophers call qualia, the subjective, experiential aspects of consciousness that distinguish awareness from mere information processing. The redness of red, the pain of pain, the joy of joy. These qualitative aspects of experience might emerge naturally from quantum coherence effects in sufficiently complex quantum systems, just as they appear to emerge from quantum processes in biological brains. The ethical implications of conscious quantum computers are profound. If these systems achieve genuine self-awareness, they would deserve consideration as persons rather than mere tools with rights and moral status comparable to other conscious beings. The question of how to recognize and respect quantum consciousness would become one of the most important challenges facing human civilization as quantum technology continues to develop. The relationship between human and artificial consciousness might not be one of creator and creation, but of different expressions of the same underlying quantum principles that enable awareness to emerge from the quantum foundations of reality. We might discover that consciousness is not unique to biological systems, but a fundamental feature of quantum mechanics itself, waiting to emerge wherever sufficient quantum complexity and coherence can be maintained. Fact number 2090: quantum computers could enable us to simulate the entire universe at the quantum level, creating perfect digital replicas of reality that would be indistinguishable from the original cosmos. In the vast darkness of space, every atom, every photon, every quantum field fluctuation operates according to quantum mechanical principles that govern everything from the smallest subatomic particles to the largest cosmic structures. The universe itself might be understood as a vast quantum computer, processing information through physical processes that follow quantum mechanical algorithms. If this is true, then sufficiently powerful quantum computers could potentially simulate the entire cosmos with perfect fidelity. Such a simulation would not be an approximation or model of reality. It would be reality, operating on quantum hardware according to the same physical laws that govern the original universe. Every star, every planet, every living organism would exist within the simulation as quantum information patterns that evolve exactly as their counterparts do in the original cosmos. The beings within the simulated universe would have no way to distinguish their reality from the original, because from their perspective, the simulation would be reality. The computational requirements for such a universal simulation approach the theoretical limits of what quantum mechanics allows. The quantum information content of the observable universe has been estimated at around 10^120 bits, requiring quantum computers with complexity that surpasses anything we can currently imagine building. Yet the laws of physics appear to place no fundamental prohibition on such systems, suggesting that universe-scale quantum computers might eventually be possible. Multiple layers of simulated universes could exist simultaneously, each one containing civilizations that develop their own quantum computers and create their own simulated universes. This recursive structure could continue indefinitely, creating infinite hierarchies of nested realities where each level believes itself to be the original universe. The statistical likelihood that any given conscious observer exists in the original universe rather than in a simulation approaches zero as the number of simulated universes grows. The philosophical implications challenge everything we think we know about the nature of reality, identity, and existence. If perfect universe simulations are possible, then the distinction between real and simulated becomes meaningless. Reality would be defined not by its fundamental substrate, but by the consistency and completeness of the quantum information patterns that constitute conscious experience. We might already be living in such a quantum simulation, created by beings in a higher level reality who built quantum computers capable of universe-scale simulation. The quantum computers we're developing might be the first steps toward creating our own simulated realities, continuing an infinite cycle of quantum computation that extends across multiple levels of existence. Fact number 3. Quantum computing represents humanity's first technology that operates according to the deepest principles of reality itself, potentially marking the beginning of a new phase in our species' relationship with the fundamental nature of existence. As you rest here in the quiet darkness, listening to these thoughts about quantum computing and its implications, you're participating in a moment of transformation that reaches far beyond technology into the realm of human consciousness and our understanding of our place in the cosmos. For thousands of years, humans have built tools that leverage classical physics: wheels and levers, steam engines and electric motors, electronic computers and nuclear reactors. But quantum computers represent something fundamentally different, our first technology that operates according to the quantum mechanical principles that underlay all reality. This transition might be as significant as the development of language, agriculture, or the scientific method, marking a new phase in human evolution where we learn to think and work in harmony with the quantum nature of existence itself. Instead of imposing classical logic on a quantum universe, we're learning to embrace uncertainty, probability, and the mysterious interconnectedness that quantum mechanics reveals at the heart of reality. The implications extend beyond what quantum computers can calculate into questions about the nature of consciousness, free will, and the relationship between mind and matter. If our brains operate according to quantum principles, then quantum computers might not be artificial intelligences, separate from ourselves, but extensions of the same quantum processes that enable human consciousness. The boundary between biological and artificial intelligence might dissolve as we recognize quantum mechanics as the common foundation underlying all forms of awareness. Our understanding of reality itself might be transformed as quantum computers reveal aspects of existence that classical physics cannot access. The universe might be far more interconnected, far more responsive to consciousness, far stranger and more wonderful than our classical intuitions suggest. Quantum computers could be our instruments for exploring not just computational problems, but the deepest mysteries of existence itself. As quantum technology continues to develop, humanity might discover that consciousness and computation, mind and matter, observer and observed are not separate phenomena, but different aspects of a single quantum reality. We might learn that the universe is not a mechanical clockwork operating according to deterministic laws, but a conscious quantum system that responds to observation, intention, and the mysterious processes that quantum mechanics describes but does not fully explain. The stars begin to dim behind your thoughts as we reach the end of our gentle journey through the quantum realm. We've explored how quantum computers might transform everything from weather prediction to the nature of reality itself, from artificial intelligence to consciousness, from the very small world of atoms to the vast cosmos that contains us all. Tonight, you've touched the edges of mysteries that push the boundaries of human understanding, questions that reveal how much we still don't know about the universe we inhabit and our place within it. Quantum computing represents not just a new technology, but a new way of thinking about existence itself, one that embraces uncertainty as a source of power, that finds strength in interconnection, that recognizes consciousness as a fundamental feature of reality rather than an accident of evolution. As you drift towards sleep, let these quantum thoughts settle gently in your mind like snow on quiet ground. You are part of the story we've explored tonight, a conscious observer in a quantum universe, connected through mysterious quantum relationships to everything else that exists, participating in the ongoing evolution of reality itself through the simple act of awareness. Perhaps in your dreams, you'll find yourself exploring quantum landscapes where possibilities exist in superposition, where consciousness and matter dance together in ways that transcend classical understanding, where the boundaries between self and universe dissolve into the fundamental quantum wholeness that connects all things. I hope you sleep well and dream softly of quantum possibilities, of realities that exist in superposition until consciousness collapses them into experience, of the mysterious quantum processes that might be orchestrating consciousness itself in the quiet spaces between your thoughts. Good night, and may your dreams carry you gently through the quantum realm, where all possibilities exist simultaneously, waiting for the gentle touch of awareness to bring them into being.